This PowerPoint is over electromagnetism. Magnetic fields are created by electricity that's moving through a circuit. So charges that are moving, that changes their electric field, and that changing electric field creates a magnetic field. Now we got two right-hand rules that we're going to be using in order to predict the direction of the magnetic field based on the direction of the current, or vice versa. First of all, we have our straight wire, where our thumb follows the direction of the straight wire and our fingers curl around. As you can see the fingers curling around on your right hand, they're going with the direction of the current. Now the thing about this is there's no north or south pole, because not all the magnetism is not concentrated into single locations like it is on a bar magnet or on an electromagnet here. So the magnetic field is simply circular around the wire with no north or south pole. The magnetic field just goes around. For this one, if you're looking above it, it goes around counterclockwise. The second right-hand rule is where your fingers follow the direction of the current. And in this example, the current comes in over here, comes over top of the ferromagnetic material, and then behind. This material right here is actually ferromagnetic. It's not a magnet. I know it says north and south, but the entire electromagnet has a north and south pole. So the fingers come over top, and then your thumb points in the direction of the magnetic field. Now the magnetic field is pointing out this end, and the magnetic field always points out of a north. So that's why we have a north pole over here and a south pole over there. So these two right-hand rules, basically what we're going to do is we're going to remember that the thumb is always following whatever's straight, and the fingers follow whatever's curled. So for a straight wire, your thumb's going to follow the current because that's what's straight, and then your fingers follow the magnetic field because that's what's coiling around the wire. And a capital B is what's used to designate magnetic field. For a coiled wire, we're going to use that the magnetic field is going to be inside of the coil, and it's going to be straight inside the coil. So we're going to use your thumb to follow the direction of the magnetic field inside the coil, and then the current is coiling around, it's circling around, so that we use our fingers in order to designate that. So the example we have here, we have a current that's going upward. If we use our right hand rule, then on this side your fingers are going to point into the page, and then on this side, as you curl your hand around, your fingers are going to point outside the page. Well, we got to come up with a way of designating inside and outside, and the way we're going to do that is to think of an arrow. If you think of an arrow, if an arrow is coming at you, coming towards you, you see a dot. So anytime you have a magnetic field coming out of the page, then you're going to use a dot in order to designate out of the page. If you have an arrow going away from you, you see the little fletchings at the end. Oftentimes there are 3 fletchings, but let's say there's 4 fletchings that make a little X at the back. So as that arrow is pointed away from you, you see the back and you see that X. So on the right side, we're going to have X's because the magnetic field is into the page, and on the left side, we're going to have dots because the magnetic field is out of the page. Now for a coiled wire, we see that our current is coming in this way, going behind and then over top. So your fingers are going to go behind the ferromagnetic material and then over top to the front. And since our fingers are following the current, that means our thumb is pointing the direction of the magnetic field, which means we're going to have a north pole over here and a south pole over there, and the magnetic field is going to come out of the north and into the south. So a couple of examples we're going to use. If you use your right hand rule here, your right hand is going to go behind the ferromagnetic material and then over top. Well, if you use your right hand, then your thumb is going to point to the right. Now that means that we're going to have a north pole at this end and a south pole at the other end, and then the magnetic field is going to come out of the north and into the south. So we got the magnetic field here coming out here and then in there, and that's what the magnetic field is going to look like for this electromagnet. In this example, we have 3 electromagnets, and these 3 electromagnets have their own current going through them. And you can see that the coil is actually in opposite directions, and the direction that the wire is being coiled actually makes a difference. So if we look at the first one, we have a current coming in here. We're going to go behind and then in front of. You take your right hand, go behind and then in front of. Your thumb's going to point to the right, which means we're going to have a north pole here and a south pole on the other end. The next one, the current's coming out over here, but we're not going to follow where it's coming out. We're going to follow where it's coming in. So again, our fingers are going to go behind and then in front of, which means our thumb again is going to point to the right. So we get a north pole on the right and a south pole on the left. Now this one, we got the current coming out here, so we're going to follow where it comes in. Now notice the wire goes in front of and then behind. So if we take your hand in front of and then curl behind the ferromagnetic material, then your thumb's going to point to the left. So we got a north over here and a south over there. We know that north and south are always going to attract, and we know that north is always going to repel, so we get attraction and repulsion. The next example, we have the magnetic field, but we need to determine the direction of the current. Well, if you hold your right hand up and have your thumb over here, because that's the direction of the north end, the magnetic field is coming out this way, so your thumb's going to be pointed to the right. So that gives a north pole over here and a south pole over there. So with your thumb pointed to the right, you see your fingers are going to go behind the ferromagnetic material and then in front of it, behind and in front. This side over here goes in front and behind, so it's not going to come in on this side. Over here it comes behind and then in front of, so that's going to be the direction that the current is going to be coming in. Some devices that we use electricity to create magnetism is a Morse code device. A Morse code device is basically a ferromagnetic material with a coil around it, and it's got a little piece of ferromagnetic material hanging above that coil, and then when you put electricity through it, it brings that ferromagnetic material, it tracks it, and it clicks with the coil that's already there, making a sound. So when you create a current, when you close the circuit by tapping on a little piece of metal to close the circuit, it creates that magnetism that causes the ferromagnetic material to attract and creates that sound. So the rate at which you connect the current, you get that same rate at which it taps with the coil and makes the sound. So you can basically take that coil and the thing that's tapping it and put it hundreds of miles away with wire connecting to your end where you're connecting it, and then that organization, the pattern that you tap and connect the circuit is going to be the pattern that's also going to be reproduced on the other end when you have the ferromagnetic material attracting to the coil. Another device, a hard drive, basically a hard drive. When you write information onto a hard drive, the hard drive has magnets in it. They're all facing in one direction, and then the electromagnet, what it does, it hovers above it, creating its own magnetism when the current flows one way, and then when you change the current flows the other way. So it either attracts or repels those little bits that are on the hard drive. So it causes them to, when they attracted, to be a 1, and when it repels, it's going to be a 0. Speakers, we have a video on the next slide I'll show you there, and then electric motors, and I'll show you one of those also.
Loudspeakers contain at least 2 magnet and cone assemblies known as drivers. They're typically housed in a box called the speaker enclosure. To build the internal magnetic structure, the factory begins by cutting 2 plates of iron, each about 13 millimeters thick. They go one at a time onto a lathe. First, the machining tool smooths and evens out the surfaces, getting rid of the marks the saw made. Then it cuts out a small hole in the center of one plate and a larger hole in the center of the other. Next, they cut a smaller and thicker round piece of iron called the core. A reamer bores a large hole through it. They apply super high-strength epoxy glue to the core and to the back plate, the plate with the smaller hole. They glue and screw the pieces together because the bond has to be strong enough to withstand intense magnetic pull. They glue a foam filter in the hole to ensure the vibrating cone doesn't draw in dust and cause internal damage. Now they spread glue on the narrow end of what's called the metal basket, a die-cast aluminum frame that will hold the magnetic structure and cone. They screw the front plate, the plate with the bigger hole, onto the glued surface. Then they glue the underside of the front plate and one side of a ferrite, a ceramic ring made from iron powder. After adhering the ferrite to the front plate, they apply glue to the other side of the ferrite, then flip the basket over to attach the back plate. The core fits through the large hole in the front plate. They insert shims to center it while the glue dries. After screwing terminals to the basket, they put the entire structure they've just assembled into a magnetizing machine. With 600 volts of direct current, the machine creates positive and negative poles, transforming the magnetic structure into a permanent magnet, meaning it has a constant magnetic field around it. Now they wind the voice coil, the electromagnet that will interact with the permanent magnet. An electromagnet is an object that generates a magnetic field only when there's a current running through it. They wind enamel-insulated copper wire, gluing it to a rigid plastic sheet. The positive pole of this voice coil will be attracted to the negative pole of the permanent magnet. The negative poles will repel each other. The key is that the voice coil's poles are constantly reversing position because the electrical current running to the speaker is an alternating current, meaning it switches between a positive and negative charge several times per second. This makes the magnets attract and repel each other continuously, causing the voice coil to move back and forth rapidly. This vibrates the cone, which creates sound waves. After slipping the voice coil between the front plate and the core, they glue on the bottom suspension, flexible fabric rings that move with the voice coil and prevent it from rubbing on the magnetic structure. Next, they glue the cone. It's usually made of cardboard, plastic, or metal. Then they solder the electrical connections. The current coming from the amplifier travels by wire to the two terminals. The terminal wires connect to the voice coil wires. After making sure the cone moves freely without rubbing, they glue on a rigid cardboard cap to keep out dust. The last step is to take the speaker for an audio test drive. They connect it to a machine that transmits different frequencies. They make sure the movement of the voice coil and cone isn't obstructed in any way. Then a computer device analyzes the sound wave the driver sends out. Two-way speaker systems have two drivers in each enclosure, a woofer and a tweeter. A woofer has a large cone that vibrates more slowly for low frequencies. A tweeter has a small cone that vibrates quickly for high frequencies. Three-way systems have a third driver with a medium-sized cone for the mid-ranges.
So here we have an electric motor. Essentially we have a coil inside of a magnetic field. Now if we attach electricity to this, basically what's going to happen is that coil of wire is going to create a current, and that current is going to create a magnetic field that's going to try to align with a magnetic field that's already here. Well, what happens is as this starts to turn to align, you can see that the connections are actually going to switch. Well, if the connections switch, then that means the magnetic field is going to switch also. So this thing is turning, trying to align with the magnetic field. Then the current switches, which means that now the poles are switched, so it's going to turn again to try to align with the magnetic field. But as that happens, the connection switches again, which changes the magnetic field. So it keeps continuing to turn, trying to align its magnetic field, but every time it tries to align its magnetic field, the connection switches, so it continues to turn over and over again. So you hook up a power supply to this, and you get some mechanical energy out because it continues to turn over and over again. Electric motors, all electric motors, are basically this design where you have some sort of magnet here, magnetic field. Sometimes this is an electromagnet that's permanently has a north and a south, but oftentimes you also have a magnet here that has a permanent magnetic field. And then you got this coil spinning trying to align its magnetic field, but every time it does, it switches its current. And we know that electric motors are going to be converting electrical energy to mechanical energy, and that's essentially what the definition, what I'm going to use as a definition for electric motors, is a device that converts electrical energy into mechanical energy.